The value of computer graphics is well known by now. The table of numbers I have here contains a great deal of information, of course, but a graph of the information makes vivid the maxima and minima and crossing points and the general shape of the data. But how do we achieve efficient, inexpensive graphics in time sharing? The main problem in time-shared graphics is low output rates. The time-shared user is basically a typist. That is, his normal input and output is geared to low-speed printing devices, such as the teletype machine. 70 useful bits per second, or 10 characters per second, is the standard in time-sharing systems, and so our task was to use that information to its fullest, to generate rapid graphic information. The time-sharer is using a computer capable of speeds 1,000,000 times faster, but only when it is dedicated to a single task, such as moving data in its memory, writing on the high-speed printer, writing magnetic tape, reading from one of the disks on which programs are stored, or writing on the drum. In fact, if the user had complete possession of a computer like this one, he could create elaborate, rapid computer displays. He could even generate animated motion pictures on the computer. However, the price tag is far too high, 20 or 30 times as high as the timeshare system we have developed. Perhaps the most common way of getting graphical information from a timeshared computer is by using the teletype itself as a plotter. The physical position of standard printing characters makes up the graph. Since there's no extra hardware to buy, this might appear at first glance to be a cheap solution to the problem, even if the process is very, very slow. This plot has been banging away already for 4 minutes and won't be finished for another 2. But just because it is so slow, it also turns out to be quite expensive. If you buy your terminal time at $10 per hour, this graph would cost you about $1. Resolution and accuracy are nothing to write home about either. A different solution to the problem is the incremental plotter. The user must buy or rent the mechanical plotter and its associated electronics, and the timeshare system he uses must have been modified to accept the plotter. It clearly offers a vast improvement in resolution. Nevertheless, it still takes as much time as teletype plotting, and even worse, it requires far more computer billing time. The same graph on this system would cost about $4 to produce. The drawing speed is about 1/8 of an inch per second on the average. That was pretty slow, probably too slow for any of the interactive uses I want to show you later on. And it's also very expensive. That system costs 4 or 5 times as much as this teletype machine here. What one really needs is a system that's fast and inexpensive and of quite good resolution. And I think the analog plotting system that we've developed here at Dartmouth goes a long way towards meeting those needs. Time-shared computer information is normally processed by a dataset or acoustic coupler before going to the teletype machine. Our electronic control unit intercepts the information and examines it. Teletype information is merely returned to the dataset and then to the teletype machine. But plotter information is converted into the voltage signals which drive the XY recorder. Now let's draw the same graph on our analog plotter. This time, the speed is about 10 times faster, fast enough to let us show you the process from beginning to end. In fact, it would take 7 times longer just to print on the teletype, the numbers being graphed here. As you can see, resolution is quite good, and computer billing time is less than 1/10 as much as for the incremental plotter. This graph costs only about 25 cents at current rates. Occasionally, the computer will transmit a bit error. When an incremental plotter receives such an error, the rest of the plot will contain the same error. But in our analog plotting system, coordinates are absolute, not relative, and so full recovery occurs after such an error. Now let's look at some applications of time-shared graphics. The first one emphasizes the convenience of user interaction with a graphical program. It is in the form of a game in which 2 players toss projectiles back and forth at one another. There is a hill between them, and the first information required by the program is the height of the hill and the position of each player. When this has been supplied, the program draws the terrain. Here you see it drawing the hill on the left, on which the first player will reside, and now you see the hill between the two players being drawn in. And now a slight rise on the right for the other player. Next it draws in boxes representing each player. The player on the right in green, the player on the left in red. Now the player on the left selects an angle and a velocity for his first shot. He hits the hill. The player on the right chooses a higher elevation and more velocity, and his shot just misses the hill and just misses his target. Now the player on the left improves his aim and tries once more. He's shooting higher now, with more velocity. And he's on target. The game is more interesting when the two players are in satellites orbiting the Earth. We view the situation from a frame of reference rotating along with the satellites, so that they appear to be at rest. The laws of physics are strange in this frame, but the computer understands them. Now let's see what happens when the player on the left fires directly at the player on the right. The player on the right notes what's happening and shoots directly away from his target. And he very nearly hits it. Now the first player has the idea. He also shoots in the opposite direction. And is right on target. Now we see an actual computational problem in mathematical physics. It is called the eigenvalue problem. We require the solution to a certain differential equation, but not just any solution. We want one which remains near the horizontal axis as it moves off to the right. Our method of solution is one of trial and error, and here we see a sequence of trial solutions. With plotter output, we have constant visual clues as to how to make the next guess an improvement over the previous ones. At the end of the process, we have the eigenvalue accurate to 5 decimal places. Here's a problem that lends itself to graphical display. What is the electric field due to any arbitrary arrangement of electric charges? For example, 6 equal charges of alternating sign, or 4, or 2, or 1 large positive charge surrounded by 5 small negative charges. Of course, there's no law that says you have to use our system just to solve problems. Here's what happens when you turn it over to a couple of young filmmakers and a composer of electronic music.